experiment looking for high energy gamma rays, and it has observed some PV gamma rays from the galactic days. So the question that we are going to ask, whether this observation could be used to search for dark matter or not. And specifically what we have explored is the decaying dark matter scenario, and we have not found any signal for the dark matter. Rather, what we found is the stringent constraint or leading constraint in some region of the dark matter parameter space. So the talk is primarily based on this paper done in collaboration with Ranjan, Abhishek, and Akash. So with this, let me start. So this is the view of this Tibet AS-gamma experiment, which is actually situated at Tibet, China. This is Chinese-Japanese collaboration. The experiment is situated at 4,300 meters above the sea level. Effective area of the experiment is roughly 10% of the Lawrence Berkeley National Laboratory. Each of the white color thing that you could see over here is a scintillator detector. There are 597 such scintillator detector, each of having area half a meter square. So what this scintillator detector do is, once cosmic ray comes, interact in the atmosphere, it would produce a shower of particles, which is known as air shower. So the scintillator detector are trying to detect those air shower particles. As I said earlier, so Tibet AS-gamma experiments is trying to detect high energy gamma rays. So it need to have something which could differentiate between cosmic ray and gamma rays, because the cosmic ray plus is quite huge. So for that, what Tibet AS-gamma experiment does is they kind of hybridize the detector. So again, each of this black square thing that you could see over here is again a scintillator detector, and in this 4 green panel, along with scintillator detector, there are water channel muon detector which are placed underground, which are 2.4 meter underground. Why this is placed underground, that will be clear within a couple of slides. So muons of energy above 1 GeV could reach the underground and produce characteristic Cherenkov radiation. And these muon detectors are quite important to distinguish between gamma rays and cosmic rays. So this experiment has taken the, this result is based on the data which is taken from February 2014 to May 2017. So live days is 719 days. Before going to discuss how it is differentiating between gamma rays and cosmic ray, let me ask the question, what is it observing? So the short answer to that question is actually high energy gamma rays. And why you are interested in high energy gamma rays? Because gamma rays being charge neutral, it would not deflected by intergalactic magnetic field. It would just point back to the sources. So essentially, it would act as a great messenger to the astroparticle physics. So one such possible source of high energy gamma ray, namely the hadronic source, is shown over here, where let's say this is a cosmic ray source, which a priori you don't know, and cosmic ray being charged particle, it would just travels in a zigzag way and interact in an interstellar medium and essentially produce charge and neutral points. So neutral point essentially decays to photons. Once these photons reach the atmosphere, it would produce sour particles, something like this. And that's what we are trying to observe in the Tibet AS-gamma experiment. And another point that I would like to emphasize over here is, if you observe a 100 eV photon, that means that would essentially predict a galactic origin of PeV scale photon because of something called attenuation. So if a photon of energy ordered 100 eV would interact with the background photons, say for example CMB, and it would pair produce, and because of this process, there will be attenuation of photons, attenuation of high energy photons. And if a photon produced, let's say from extragalactic sources, due to this attenuation, it would not just come to us. So that's why I said, if you observe a 100 eV gamma rays, that would essentially say the galactic origin of PeV scale cosmic ray, sometimes known as Beaverton. So the bottom line here is to understand the cosmic ray physics better. Now coming back to the question of how it is differentiating between proton and proton shower. In the left panel, I saw the shower that would be induced by a primary gamma ray, and in the right panel, I saw the schematic figure for the same for the cosmic ray. So as you could see over here along with electron, positron, and gamma ray, here you have electron, positron, and gamma ray, mostly electromagnetic shower. And for the cosmic ray, along with those electron, positron, gamma ray, you also have charged kaons, muons, neutrinos, and all other things. In the case of, like, in the context of Tibet AS-gamma experiments, these muons are quite important because that's what they utilize to differentiate between cosmic ray and gamma ray shower. By looking at these two figures, one may assume that gamma ray shower doesn't produce any muons, but that is essentially not true, because occasional gamma p interaction may give rise to shower similar to this hadronic shower. So it is a painstaking job to differentiate between proton and proton shower. To emphasize the point in a bit more detail, what I am showing over here is the air shower that will be produced by 200 TeV gamma ray in the upper panel and 200 TeV proton in the lower panel. So here the red color lines represents electron, the yellow color lines represents positron, and the blue color lines represents muons. So muon doesn't lose energy that efficiently compared to electron or positron. It's sharply proportional to the probably inversely proportional to the mass of the particle. So what happens is that electron positron does lose energy efficiently, and they just cannot go through the soil. But muons can do that. So that's why you put the water Cherenkov muon detector underground. Now the other point is that if you just compare these two figures, you would see that there are lots of muons in the proton shower compared to the gamma ray shower. So what Tibet does is they kind of utilize this fact to differentiate between a cosmic ray and gamma ray shower. Further, so what I'm showing over here is in the x-axis we have the number of muons above 1 GeV, and in the y-axis we have the probability of getting that muons from a particular shower. This line shows the corresponding shower probability from the gamma ray, and this line shows the corresponding shower probability from the, let's say, proton. And in your experiment, if you put a cut over here, let's say in your experiment you are considering muons number to be less than 75, then what you are doing is roughly keeping 10% of your gamma ray flux, but your proton shower is almost reduced by 10⁻⁷. So what you essentially want to do, you want to keep most of your gamma ray flux and get rid of the cosmic ray or the background proton flux. So for that, what you need to do is you need to put the optimized cut. Once you put optimized cut, you get rid of most of the proton, and what you are essentially left with is a gamma ray flux. So that's what Tibet does. And after the optimized muon cut, the survival ratio for the photon is almost around ordered 1 number, but the corresponding number for the proton in the energy regime of operation of Tibet, which is ordered 100 TeV or so, is around roughly around 10⁻⁶. So the proton shower is muon rich as compared to the gamma ray shower, and the spectrum of the muons that are produced by gamma and proton shower is quite different. So Tibet utilized this fact to differentiate between cosmic ray and gamma ray shower. Along with this, what Tibet can do is it can also track the direction from which the photons are coming by looking at the timing information. So in the first 3 panel, the experimental collaboration has presented their result for 3 energy window, 3 chosen energy window of operation. For the first one is for 100 to 158 TeV, second one is 158 to 398 TeV, and the third one is 398 to 1000 TeV. For each of these figures, the shaded region is the region where Tibet cannot look at. If you put a telescope at any point, some region of the sky will be just beyond your horizon. So this shaded region represents that region. And this black solid lines represents the galactic plane. And each of these blue points in these 3 panels represents each of these points actually represents gamma ray-like events. And as you could see, there are lots of points in the lowest energy beam. And as your energy is increasing, the number of points is actually decreasing. That is kind of expected. And also, if you just look at this third beam, you'll see that along with blue dot points, there are also red cross point, which actually represents known TeV sources. What their claim is that most of the gamma ray-like events that they are observing are not matching with known TeV sources. So that's why the gamma ray like events that they are observing are not associated with any sources, so that they are kind of orphaned. That's how we define the diffuse gamma ray events. So I mean, just to be more clear about it, so what have been plotted here in the x-axis is the distance to the closest TV sources and number of events in the y-axis. As you could see, the distance to the closest TV sources is almost 1 degree in the sky. This is kind of a angular distance. You can convert it in linear distance also. So what Tibet has observed is the gamma rays, and the gamma ray events that they are observing are not associated with any sources. So that's why they call it as a diffuse gamma ray events. Now, the next question one may ask, what is actually like gamma ray flux that they have observed? For that, this is how the collaboration has presented their result. So for both of these plot, energy is plotted in the x-axis and differential gamma ray flux is plotted in the y-axis. The red dotted points shown in both of these plots are what have been observed by Tibet AS-gamma experiments, with the corresponding representative energy is given by these three values: 121 TeV, 220 TeV, and 534 TeV. And the black solid lines actually represents the gamma ray flux that have been predicted by different cosmic ray theoretical models. For instance, the black solid lines represents the gamma ray flux that have been predicted by space-independent cosmic ray model, and the dashed line represents the gamma ray flux that have been predicted by space-dependent cosmic ray model. So this blue color points over here represents the gamma ray, like the diffuse gamma ray flux that have been measured by Argo IISc experiment. As you could see, even within 2 decades, there are no observation. So what it essentially suggests, this is the first detection of sub-TeV diffuse gamma rays. And for for this panel also, this red points again represents what have been observed by Tibet AS-gamma experiment. The down-headed arrow thing is the upper limit in the gamma ray flux that have been given by this Kasami experiment. They have not observed anything. That's why they put upper limit in the gamma ray flux. And again, this the different black color lines represents gamma ray flux that have been predicted by different cosmic ray theoretical models. So even after like experimental collaboration has presented their result, there are some theory paper which actually kind of try to see what kind of cosmic ray models would fit the data, and roughly most of the models are kind of fitting the data. They are kind of producing a band over the data itself. So they have observed the diffuse gamma ray flux, and most of the prior theoretical expectation kind of roughly matches with the data. So given this situation, the question that we are going to ask is whether we could search for dark matter or not utilizing this observation. Especially we'll be looking for the decaying dark matter scenario, where the dark matter is decaying to 2 body standard final state. And we do not find any signal for the dark matter. Rather, what we find is the stringent constant on the dark matter parameter space. So let's say chi is the dark matter, which is decaying to any 2 body standard state. Let's say it is decaying to 2 quarks. So I mean, the underlying particle physics model like depends on what kind of models that you are writing over here. I would not be talking about any particular model over here. Rather, I'd be taking a model independent approach. What I'll be saying is, let's say chi is the dark matter, which is decaying to any of these 2 standard model states. Let's say this is decaying to 2 quarks. Then what may happen is that this quarks gets hadronized to produce pions, and that essentially decays to 2 gamma rays. The spectrum of the gamma rays could be calculated utilizing either any of the publicly available code like ASTM spectra, PVPC. We have utilized the gamma ray spectra that have been given by this ASTM spectra. The other thing is that that I have not discussed is the attenuation, which actually says, let's say this is the gamma ray that are produced by the dark matter decay. And what may happen is that this gamma ray interact with some background photon, which could be either CMB or could be starlight or could be infrared. And once this gamma ray interact with background photon, it would essentially produce 2 electron projectons. And because of this process, there will be reduction in the gamma ray flux. Like while it coming from the source to your detector, due to this pair protection process, there will be attenuation or there will be reduction in the gamma ray flux. And essentially, you could calculate utilizing this formula if the path length or the length that the gamma ray are traveling is much larger than the length of the mean free path of the gamma rays, then there will be reduction. If larger than the mean free path, then there will be reduction in the gamma ray flux, and if it is much more smaller than the mean free path of the gamma rays, then there would not be any reduction in the gamma ray flux. So, and the mean free path could be calculated utilizing this formula, where NB is the background photon number density and sigma gamma gamma is the gamma gamma interaction cross section. So if you just take CMB as the background photon, then the corresponding attenuation is given in this plot, where in the x-axis we have the gamma ray energy, and in the y-axis we have the attenuation factor. As you could see, as the length is increasing, as the L is increasing, the attenuation due to the CMB is actually increasing. Now, our nearest galaxy is Andromeda galaxy, which is roughly 750 kiloparsec away. Now, if you take this L as 750 kiloparsec away, in the energy regime of operation where Tibet is operating, the attenuation will be quite huge. So that's why I said, if you observe or in the order 100 TeV regime, the attenuation will be quite huge. So that's why I said a 100 TeV photon must originate within our galaxy. So this is due to the, this attenuation is due to the CMB. In principle, one can do this same thing also for starlight and infrared. The region that Tibet is looking at, there, it is not really looking at the galactic center. So starlight, infrared are quite dense near the galactic center. So in our numerical calculation, starlight and the attenuation due to the starlight and infrared are not really important. So that's why we have neglected that part. So we have only included the CMB part. Once you have all these things, then what you could do is you could actually calculate what could be your gamma ray flux that is coming from the dark matter itself. So that can be calculated utilizing this equation, where delta omega is your region of view of the experiment. This is the differential gamma ray flux. So delta omega is the region of view of your experiment. MK is the dark matter mass. Tau K is the dark matter lifetime. This is the spectra that I have just discussed. And then you have the line of sight integration. So for the line of sight integration, you need to have knowledge of dark matter density profile, for which we have taken the well-known NFW profile. And as I said, this attenuation factor is just the reduction in the gamma ray flux, depending on what kind of background photon site you are considering. So once you have this, you can calculate what is your gamma ray flux that are coming from dark matter. As I said earlier, so cosmic ray physics is there. We don't know which of the model is true, like which of the cosmic ray physics is giving you the true model. That's why you have taken 3 different benchmark model for the cosmic rays: the space independent cosmic ray model, space dependent hybrid gamma ray model. In space dependent, you assume that the gamma ray spectrum is same throughout your galaxy. For space independent case, you assume that the gamma ray spectrum is almost constant throughout our galaxy. But for the space dependent constant, you do not assume that. And there are several other assumptions which is given in this paper also. And for the hybrid gamma ray, what you do is you kind of, along with hadronic contribution to the gamma rays, you would also include the leptonic contribution coming from the inverse concurrent itself. So the point over here is, what you need to do is you need to add up the gamma ray flux that are coming from the dark matter and from the background, and then you need to check the dark matter parameter space where this addition of these two are less than the data, which is given over here. These are the kind of 3 representative energy that I was talking about earlier, and these are the kind of gamma ray flux that have been given by the collaboration itself. So once you do this, for doing this, what we do is we actually did a simple chi-square analysis. So again, what have been plotted here is the dark matter mass is in the y-axis, and dark matter lifetime in the dark matter mass in the x-axis, dark matter lifetime in the y-axis, and this is for a particular decay channel where dark matter is taken to BB bar. And these 3 different solid lines is actually corresponds to the 3 different solid lines represents the limit that are coming if you take these 3 different background cosmic ray models. And this dashed line is the limits that were already there in the literature. So what essentially it suggests is that if these are the true model for the this hybrid gamma ray model and space dependent model are this blue and green line are the kind of two different background true model for the background cosmic ray things. Then this is the new region of the parameter space that you are probing through this data. Note that for the combined Freebius limit, the lowest, for these masses, the limits are mostly coming from the Fermi, and here it is coming mostly from the IceCube data. So with this new observation, there is a possibility to probe new region of the parameter space depending on the what cosmic ray model is true. While here I like this things talk about the thing where dark matter is decaying to BB bar. We have also explored some other channels where dark matter is dipping to like some other final state like tau plus tau minus, and also various different final state. Our conclusion is that except for first two generation of leptons, our bounds are stronger than the previous bounds. And as I have assumed, I've said earlier, we have assumed the dark matter profile to be NFW. Since the Tibet is not really looking at the galactic center, so that's why these dark matter density profiles are really different near the galactic center. So since the Tibet is not looking at the galactic center, so that's why our bound doesn't really depends on what kind of dark matter density profile, whether it is core profile or cosmic profile. Depending on that, our result doesn't change. So that in that sense, you would say that it is robust. So this is up to the point, like this is up to the 2105. Then there is an update which is given by Lasso. Very recently, Lasso has published their result where they have searched for the same scenario where dark matter is decaying to toward the final state, and this black line represents their data, which is a factor of few stronger than our results. So instead of an update, I would rather say it an interesting update, because this shows that within even 1.5 years, our limits are kind of outdated, and this shows that the field is growing very rapidly. And since you are probing new region of the dark matter parameter space, possibly with near future data, you might be able to see the signal for the dark matter. So with this, let me conclude. Recently, Tibet AS-gamma experiment, which is a round-based experiment, has observed sub-PV gamma rays from the galactic disk. We have utilized this observation to search for decaying dark matter, heavy decaying dark matter scenario. We do not find any signal for the dark matter, rather we find in the stringent constant of the dark matter parameter space. And since we are kept on probing new region of the dark matter parameter space, possibly with near future data, we might be able to see for the signature of the dark matter. With this, I stop here. I'm happy to take questions now.
Yeah. Thank you very much for this very nice talk. Are there any questions for him? I can see some hands. George, can you please unmute yourself?
Yes, thank you for the talk. Very interesting. So I'm just wondering, what are the possible? Is this diffuse PEV gamma ray flux consistent with what we know about the spectrum of cosmic rays in the galaxy?
So what you are saying is the so let me go back to, so first of all, what you are doing over here is the cosmic ray flux, that is the, let's say, proton and other element flux that we are trying to get rid of. Okay, now what you are observing over here is the gamma ray flux. Now people have written like different model for this gamma ray flux that could appear from the like cosmic ray itself. So these are the kinds of those models, like gamma ray flux, that have been predicted by different cosmic ray theoretical models. So my essential point is that if like different people have written different kind of models, if you take the, let's say, space independent cosmic ray model as a true model, then this is what that model predicts, and it is roughly matches with your data. And if you look at these papers also, they have like proposed different kind of model where they have taken different propagation and different all other effects. And they have also shown that, I mean, essentially what they shown is the kind of, instead of a single line, they shown a band, and the band is actually passing through your data. So that essentially says is roughly whatever we have, whatever our expectation was, that is matching the data. Does that answer your question? Or?
Yeah, thank you. I guess I'm, so the pulsars, say millisecond pulsars, for example, can't account for these really high energy photons. Is that correct?
Yes, exactly. That's what this pulsar halo model says.
Very good. Thank you.
Exactly. Yeah.
Any further questions for Tarak? I don't see any more hand. So maybe we can thank the speaker again for this wonderful talk, and we will meet next week.
Okay. Thanks. Thank you all. Thank you for attending.
Thank you.
Thank you.
Thank you very much.
Okay, so maybe I should stop the recording.